Welcome to the R-Lab video on subset selection methods. In this video, we're going to talk about subset selection methods in R. So first thing we're going to do is load the Isler library, walking through the lab for chapter 6. So execute the command. Now we're going to work with the hitters data set. We're going to be predicting salary as a function of the statistics for the different ball players. So we want to do some fixing and repairs on that data set. Open up my window a little bit. So we can look at the names of the variables, at-bats, hits, home runs, runs. If we wanted more information about this, we could get more information by doing question mark hitters. And one of the things you'll notice is RBI is runs batted in, CRBI is career runs batted in. RBI itself is runs batted in 1986, the previous year for this data. So dimension of hitters, we have 322 observations and 20 variables. We want to look at how often there's a NAN in the salary. We want to omit those entries. And now we have 263 observations left and 20 variables. And there's no more NANs present. We're going to read in the library leaps and do this regression fit in the library leaps. Salary as a function of all the inputs. And then we can do a summary. Expand this a little bit and execute that command again. So this is doing a search through the possible models. There we go. And it is telling us the best model at each size. So the best model of size 1, meaning there's one input variable, includes just career RBI. So that's the most important variable if we were looking at only one variable. If we're looking at two variables, we go to the second row in this table. And we see across the second row that we want the hits and career RBIs. So hits last year and career RBIs. Third best model, or the best model that includes 3 explanatory variables or 3 regressor variables, has hits, career RBIs, and the number of putouts, and then so on down the list. So that's the information that this library is giving us. Remember, when we're comparing different models of the same size, meaning the same number of variables, we can just use residual sum of squares to compare them. So we don't have to use BIC or AIC. And then when we compare among these best models, we have to use BIC or AIC or something adjusted R squared, something a little more sophisticated that requires a little more computation. So we can look through, execute the regression again, and then we look at the names that are output to us in this regression summary. And one of the output names is R squared. And so now we can look at the output that's included in the R squared. So that tells us the R squared values for the best models. And you notice they're going up as we go left to right across the first row. This is in order of model size. So this first number, 0.32, that's the R squared for a single element model. 0.425, that's the R squared for 2 elements, and they're increasing monotonically. That's always going to be the case because as you increase the size of your model, you will be getting better fit. And so we are going to do some plots, and we are going to look at, let's just take a little heads up of what we were going to be plotting. We're going to look at residual sum of squares. As we just looked over in that table, we're going to plot that, and then we are going to look at adjusted R squared, and then we're going to look at the CP value and a number of these different metrics across our top models. It's going to come out in this plot, and it's going to be a little bit crowded, so I'm making room, just squishing our text a little bit. Here we go. So, okay. So this is on the horizontal axis number of variables, and the vertical axis RSS, and we see, as we observed before, the residual sum of squares error decreases monotonically with the number of variables. That's one of the reasons we can't use residual sum of squares to compare across models of different size. This is a plot of adjusted R squared for the different models, and we can ask which model gives us the highest adjusted R squared. Remember, adjusted R squared, higher is better, closer to 1. And so the model of size 11 gave us the best adjusted R squared. So we can put a red dot right at that location. We're going to plot number of variables as a function on the horizontal axis, and then CP on the vertical axis as a function of number of variables. And then the best model was the model of size 10. And so adjusted R squared and CP are giving us the same model as the best model. And our best model using BIC is the model of size 6. And so there's a plot of BIC as a function of the number of variables. And you see size 6 is right there. And it looks like size 8, according to BIC, is almost as good as size 6. And so one of the things that we've talked about is BIC will tend to give you smaller models. It tends to put a larger penalty on the model size. So now what we're going to do is create some plots. Let's get these 4 plots up, and then we'll look at this in full scale. And zoom. It'll allow us to see these plots a little bit better. In each of these plots, the horizontal axis goes through the different features, the input features. The vertical axis gives us the value for our metric for evaluating the linear mixture models. Across the top, we have these sorted by the evaluation metric, R squared, adjusted R squared, down here in BIC. And then the black squares tell us which explanatory variables or regressive variables were included in that model. The darkness tells us how good that model is by this evaluation metric. So for example, here in BIC, our top model has an intercept, number of at-bats, number of hits, number of walks, career RBIs, and then putouts, or no, division wins and putouts. The next best model, how does it change? It includes career home runs, it includes career runs, it removes career RBIs, and it includes career walks. And so you can go down the list. One of the things to observe with BIC is we have a number with around a negative 150 as their BIC score. So these models are close in their evaluation and how good they are. They're close to each other. This is an example where some model averaging that we talked about might be useful to get some better understanding, because we have multiple good models that are competing with each other. And so this is a look at the best model as evaluated by Bayesian information criteria. And so the intercept has a value of 91. And remember, we're predicting salary as a function of these different input variables. At-bats, number of at-bats, has a negative coefficient. Apparently, when you're including all of these things, your number of at-bats is negatively correlated to the, it's not that it's negatively correlated, in the presence of these other ones. So you want to have a lot of hits over a few at-bats. So that may be why this is giving you a negative coefficient. Hits has a 7, walks is, you can read the coefficients as you go across. Okay, so now we're going to look at some Bayesian model averaging. So this is a block of code that I added using Bayesian model averaging to get a better understanding. So the standard code for the lab for the textbook doesn't have this small segment, and I'll show you what we're going to add here. Just these 5 lines. So we add the library, and first thing we're going to do is we're going to run Bayesian model averaging on the, well, let's do the headers data set that we were just looking at. So we create our beta model averaging. And it takes a second because it has to create lots and lots of models to compete them against each other and compute their probabilities. And then we can look at the regression model that we get. And so these are the probabilities for the different regressive variables. So at bat has a probability of 0.81, hits has a probability of 0.88. And so we can look at the probabilities that these different regressive variables should be included, and those probabilities were averaged over those multiple top models. And we saw that there were multiple top models that had different combinations of regressive variables, different importances. We can look at the probabilities for the top few models. And so this column tells us the probability for these variables. This is model 1, and this tells us whether this variable was included in that model or not. So here's the top 5 models, and these are similar to what we saw in that plot when we looked at it before. We looked at the top 2, here's the top 5, and then we do model averaging over the top 5 and gives us these probabilities. If we cared about those individual metrics, these probabilities would be a very useful way to measure how probable those metrics are in contributing to the being present or contributing to salary. So we're going to work with another data set that we've seen a lot, this sales as a function of TV and radio and newspaper. This is the main data set that we looked at. We looked at the lesson video for model selection. And so let's create a model using that. Oh, we have to load that in. This is the location on my computer where I have the advertising data saved. So you might have a different location there. Then we'll do our Bayesian model averaging, and then here's our summary. Model 1, the best model, has the intercept, the TV, and the radio, but not the newspaper. And then when we read down here, this row, best post probabilities, the probability that this model is the correct model is 0.88. So it's 0.889. So it's 89% probability. Model 2, this is the model that has TV, intercept, radio, and newspaper included, and that has a significant drop in probability. So we would say this model, model 1, is much more probable than model 2, which includes the newspaper. But that model, which includes the newspaper advertising, we can't eliminate it outright. There's a non-zero probability. The probabilities for the rest of these models, they're so small, they're insignificant. So that gives us one perspective on how probable these different models are and how probable it is that the newspaper is an important variable. So these are the probabilities for the different variables. One for intercept, one for TV, one for radio. Probability for newspaper is 0.11. And that completes our R video looking at model selection in the R lab. Thank you very much.